In this video, we're going to introduce the idea of a binary operation on a set and the idea of a Cayley table. So first, let's start with what a binary operation is. So suppose I have a set S. So I'm given a set S. A binary operation on S is technically a function, and I'm going to call it star, from the Cartesian product of S with itself to S. Okay, so just in case you're not overly familiar with this type of notation, this is going to be the name of my function. I'm actually going to call the function star, and the star takes as input any pair of elements of S, an ordered pair of elements of S, and produces a single element of S as an output or answer. Now, whether you realize it or not, you actually have quite a bit of experience with binary operations. For example, there are some binary operations on the real numbers with which you're probably familiar. So these are some examples of binary operations on the real numbers. So there's one called plus, which takes an ordered pair of real numbers and outputs a real number. And the way that we usually write that in practice is we say something like, okay, well, if I want to operate on 3 and 5, that is, I want to perform addition on 3 and 5, I get 8. That's actually not the common way of writing that. The common way of writing that is to say 3 plus 5 equals 8. So this is actually a more traditional use of function notation. If we're thinking of this as a function, we put the function name here and then put the inputs in parentheses and put the output here. But the way that we usually do this with a binary operation, the way that we write down a fact involving that binary operation, is to put the name of the function or the operation in the middle of the two things we're operating on, and then put the output over here. Okay, so that's one binary operation. Here's another binary operation. It's called subtraction. Again, the input is any ordered pair of real numbers. So I could subtract, for example, 2.5 and 7. And what would I get? I would get 2.5 minus 7 is negative 4.5. So equivalently, I could say that the result of this subtraction is negative 4.5. There's also multiplication, which I'll just represent by dot. There's dot from ordered pairs of real numbers to real numbers. So the result of multiplying, for example, 3 halves and 12 would be 18, though usually we would write simply that 3 halves times 12 equals 18. Okay, and you may be thinking, oh, but there's one more. There's division from ordered pairs of real numbers to real numbers. But wait, that's actually problematic. That's actually not a binary operation in the same way that the other ones are, because a function should be able to take any possible input from our domain, so any ordered pair, in this case of real numbers, and produce a real number. And that's not always possible here, because suppose I wrote down the result of division on, let's say, 2 and 0. Well, I wouldn't get anything in particular. My answer or output would be undefined. So that means that I could define division as a binary operation, but it would have to be on some set other than just the real numbers. Okay, but I do have at least these 3 possible examples of binary operations on real numbers. Okay, so that's a basic idea of what a binary operation is. Now here's another example of a binary operation. Another example would be on this set, which is called the integers mod 5. The idea of the integers mod 5 is we sort of imagine ourselves counting on the face of a clock, except instead of having 12 markings, the clock has a total of 5 markings. And we call these 0, 1, 2, 3, and 4. And there's actually a more formal way than this of defining z mod 5, but we're going to use this more informal way here, just as a way of establishing another example of a binary operation. So the way that we count in z mod 5 is we start at 0, and then counting up we go to 1, and then 2, and then 3, and then 4, and then counting up again gets us back to 0, and then 1 again, and then 2 again, and so on. So rather than counting up continuously along a line, we're counting around a circle. The way that we add in z mod 5, or the integers mod 5, is sort of like this. So here's an example. Suppose I want to add 3 and 4 in z mod 5. Well, the way that I would do that if I were just adding these as whole numbers, never mind z mod 5, would be to start at 3 and then count up 4 times. So I go 3 and then count up 4 times. 4, 5, 6, 7, and then my answer would be 7. But here I'm going to start at 3 and then count up 4 times. I'm going to go 4, 0, 1, 2, and that means that my output or answer is 2. Okay, so remember, these represent elements of z mod 5, not ordinary integers. So in z mod 5, the result of adding 3 and 4 is 2. Let's try a different one. The result of adding 4 and 2, well, I could start at 4 and then count up by 2, 1, 2, and I end up at 1. So in z mod 5, or the integers mod 5, 4 plus 2 is equal to 1. And then some addition facts work out sort of the way that we're used to, like 2 plus 2. Well, if I start at 2 and then I count up by 2, there's nothing going on there that's going to make the answer to that addition anything other than what we're used to. So the answer to 2 plus 2 is still 4. Okay, so some things are still the way that we're used to. But the reason I'm introducing this operation, so this is an operation on a finite set, because this set only contains 5 elements, 0, 1, 2, 3, and 4. That's the entire number system. And I have my idea of addition over here. I mean, these 3 facts don't count as a definition, but what I said earlier about counting up sort of does qualify as a definition. So what we could do is we could actually build what's called a Cayley table for addition in z mod 5. And here I want to be a little bit cautious because I think that we use the phrase Cayley table only to refer to operation tables for a group, for something that ends up being a group. We're going to talk about what a group is in a subsequent video, but for now I will just state as a fact that this operation, under this operation of addition, z mod 5 is a group. So therefore we're justified in calling this a Cayley table. So here's how we build a Cayley table. We first of all create a lot of room because we're going to be making a 5 by 5 table. Alright, so what is a Cayley table anyway? A Cayley table is just an operation table that tells us the result of operating on any 2 elements of our set. And this is actually why I introduced z mod 5. I could have proposed to give you a Cayley table or an addition table, for example, for the real numbers, but that would have taken a very long time. Okay, so what I'm going to do is I'm just going to list all of the elements of this set, z mod 5, 0, 1, 2, 3, 4, up here and down here. Okay, there we go. And I'll try and make some grid lines here. Probably I should have done this a little bit neater by doing it in Paint or something, but I think this will work okay. There we go, that's not half bad. Alright, so now we have room to create a 5 by 5 table that shows the result of any possible addition that we might do. Now, one distinction I'm going to make that's going to be more important later, because in this system, and really in just about any system we might talk about, addition is a commutative operation. So it doesn't matter whether we think of this space, for example, as being 2 plus 3 or 3 plus 2, but I actually do want to insist that we call this space the space for 2 plus 3. So the operand that goes on the left is over here on the left side, and the operand that comes after is up here. So for example, if I'm going to record the fact that 3 plus 4 is equal to 2, I'm going to put that in this space here. 3 plus 4 equals 2. Alright, so we can go ahead and record the results of all of the operations. First of all, operating with 0, adding 0 is usually pretty easy to do. 0 plus anything is whatever that thing is. Anything plus 0 is whatever that thing is. So I can go ahead and report the results of all of these operations in the table. Okay, so for example, this space here says 3 plus 0 is 3. This space says 0 plus 2 is 2. Okay, and then there are some other ones that are just familiar to us and don't really involve having to count beyond 4 on the clock, like 1 plus 1 is 2, 1 plus 2 is 3, 1 plus 3 is 4. Let's see, 2 plus 1 is 3, 3 plus 1 is 4, 2 plus 2 is 4. Okay, after that things get kind of interesting. For example, what is 1 plus 4? Well, to find 1 plus 4, I start at 1 and I count up 4. 1, 2, 3, 4. I land at 0. So that means the 1 plus 4 is going to be 0. And similarly, to find 4 plus 1, I can start at 4 and then count up 1, that also puts me at 0. It's not obvious that those two processes should result in the same answer all of the time, but in fact they do actually do that. 3 plus 2 similarly is going to be, let's see, start at 3, count up 2, 1, 2, 3 plus 2 is 0. So we got that. 2 plus 3 is also 0. And I'm just going to go ahead and record the rest of these. These are all going to be 1. This makes kind of a nice pattern. 4 plus 3 is 2. 4 plus 4 is, well, let's just check it. 4 plus 4 is, start here, count up, 1, 2, 3, 4. 4 plus 4 is 3. All right, so there we go. So this is a Cayley table for Z mod 5 under addition. All right. We're going to talk about some things that we can discern from a Cayley table, some properties of this operation later, but I think this is a good start. So now we know what a binary operation is. It's a function that takes two entries or two members of a set and produces one member of a set, which is the output or the result of that operation, and we know how to build a table for an operation.